We're now going to take a look at the proof of the power rule when n is a positive integer. So remember, the power rule states that the derivative of x to the n is n x to the n minus 1. All you do is drop a copy of the exponent down in front of the x and then subtract 1 from the exponent, and that gives you the derivative of x to the nth power. Now we're going to prove this for n being a positive integer. The other cases when n is a negative integer or a rational number or an irrational number, those will have to wait until we have more results that are available to us to prove those cases. So let's start with our proof down here. So now we're first going to look at the case when n is a positive integer bigger than or equal to 2. We'll do the case when n is 1 separately. Now let's notice a pattern that we have when we look at x plus y to the nth power, when we expand that out. So first of all, if we look at x plus y squared and we FOIL that out, notice that you get x squared plus 2xy plus y squared, right? Now notice something. Notice how the 2 here in this exponent matches with the 2 right here. And also notice that we have an x to the 1 and a y to the 1 power. 1 plus 1 gives you 2. And then all the other exponents are 2 as well. Now if we look at x plus y cubed, you will get x cubed plus 3x squared y plus 3xy squared plus y cubed. That's what you would get. Notice also how you have this 3 right here matches with the exponent right there. And notice also, you see you have an x to the 2 power here. Notice that right there, that 2 is 3 minus 1. And then you have powers of y out here. Now if you look at x plus y to the 4th power, that's going to be x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. And notice the pattern here. Notice how you have that 4 right there, a 4 in the exponent here. Notice that the x, the power of x, is 3 here in this case, and notice that that 3 comes from 4 minus 1. For the 5th, notice that you're going to have x to the 5th plus 5x to the 4th times y. Notice you have that pattern. You got the 5 here and the 5 here. The x to the 4th, that 4 is 5 minus 1. And then you have out here, you just have higher powers involving the y's. Now these coefficients, the 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. There's a formula that we have for those. Those are actually called our binomial coefficients. And they actually also come from, interestingly enough, what's called Pascal's triangle. That's a very interesting thing to look up if you're interested in that. You can recover these coefficients by looking at a triangular pattern of numbers. Very interesting. But we don't need to look at that right now. We just need to notice this pattern with those coefficients there, the 2. Notice 2x to the 1, 3x squared, 4x cubed, 5x to the 4th. Alright, now in general what we have then is if we look at x plus y to the nth power, you're going to get x to the nth power. That's the very first term here being raised to the nth power. And then just like we did up here, you're going to have an n times x to the n minus 1 times y to the 1 power. And then all of these other terms out here are just going to be higher powers of y. They're going to be, y raised to some power m, where m is bigger than or equal to 2. Alright, that's all they're going to be. And you have coefficients that go in front of them. And there's a formula that you could look into that will evaluate those coefficients. Now, if you replace the y with a delta x, what we would get then is x plus delta x to the nth power is x to the nth power. Then you'd get n x to the n minus 1 times delta x. Right here would be your next term. And then out here, you would just have higher powers involving delta x's. So these would all be delta x squared, delta x cubed to the fourth, and so on. Just all higher powers of delta x. So you'd have delta x's raised to some power where that m is bigger than or equal to 2. All right. Now we can continue. Now we're in position to actually prove this result, making this observation here. All right, so here we go. So we begin with looking at the derivative of x to the n. Now we have to go back to the limit definition. So this is the limit as delta x approaches 0, f of x plus delta x minus f of x over delta x. And we replace the f of x with x to the n, f of x plus delta x, that's x plus delta x to the n. And now what we do is we expand out the x plus delta x to the n, noting this observation up here. So we use this in place of the x plus delta x to the nth power, and we get this down here. Now notice that we have some cancellation here. Notice this x to the n cancels with that one. And then we get this down here. Now if you notice, every term here, here's a delta x to the 1 power, delta x squared, dot dot dot, delta x to the n minus 2, delta x to the n minus 1, delta x to the n. Every term here has a delta x in it, so we'll cancel it with the 1 in the bottom. So this just becomes the number 1. This becomes just delta x to the 1 power. This becomes delta x to the n minus 3, n minus 2, and then just n minus 1. And we end up with this down here then. Now if you look at this, every term here has a delta x in it, this one, and all of these out here, except for the very first term right here. That does not involve any delta x's because it was completely canceled out up here. So all of these terms here, they are all going to 0 as delta x approaches 0. And so we're left with, in the limit, n x to the n minus 1, and there's the proof for n bigger than or equal to 2, n being an integer. That's the proof of the power rule in that case. Now if n is equal to 1, that's a very simple case. You look at d dx of x, that's just limit as delta x approaches 0, x times delta x minus x over delta x. Of course these x's here cancel out. You get the limit as delta x approaches 0, delta x over delta x, which of course is just 1. And that can be written as 1 times x to the 0 power. Remember, any number to the 0 power, that's equal to 1. So x to the 0, that's just 1. And so we see that the rule holds in the case when n is 1. So the derivative of x to the 1 is 1 x to the 0, which is just 1. All right, so it holds for n equaling 1 as well. So that's a special case to remember. d dx of x is just 1. All right. And that proves the power rule for the case of n being a positive integer. Now we'll have to look at the other cases later as we have more results available to us.